temperature and their relation to energy and work. It defines macroscopic variables such as internal energy, entropy, and pressure that partly describe a body of matter or radiation. Thermodynamics describes the bulk of behavior of the body, not the microscopic behaviors of the very large numbers of its microscopic constituents, such as molecules. Thermodynamics is concerned with the amount of work and amount of heat that a system takes in and outputs. There are different processes involved in thermodynamics depending on what the system is undergoing. An isochoric process is one in which the volume is constant, while an isobaric process is one in which the pressure is constant. An isothermic process is one where the temperature remains the same. Thermodynamics is concerned with the amount of heat and work that a system goes under. Heat is defined as energy transfer without mass transfer due to temperature difference between the system and the surroundings. When the heat is greater than 0, that means the heat is going from the surroundings into the system, which means work is being done on the surroundings by the system. When the work and heat are negative, heat from the system goes into the surroundings, which means work is being done on the system by the surroundings. When looking into thermodynamics, there are 3 types of systems that you need to take into account: open, closed, and isolated. An open system is when energy is transferred as well as mass, like a cup of coffee. A closed system is the one that we'll be focusing on most in thermodynamics, and is when mass is not transferred but heat is, like a thermos. An isolated system is a very uncommon type of system, and there's really only one possibly known system that's isolated: the universe, because nothing is transferred in or out unless there's another multiverse that we're not sure of.
Because closed systems are the most common system in thermodynamics, today we'll be looking at a heat engine. There are 2 major parts to this system. The first one we are examining is the heat reservoir. This component of the system is so large in relation to the engine that it does not matter if the engine uses energy from it or releases energy into it. The heat reservoir's temperature will not change. There are 2 reservoirs in the system, a hot one and a cold one. The second part of the system that we will examine is the heat engine itself. While it may be more complicated than the diagram suggests, for all intents and purposes, it is the component that does the actual work for the system. With this simplified diagram, we can write an energy equation. Because of the law of energy, the conservation of energy, we know that the energy that goes into the system must be equal to the energy coming out of this system. Breaking this down further, we know that QH is the energy supplied by the heat reservoir is the energy input, whereas the energy output is the work done by the system and the energy lost to the cold heat reservoir. Now when you add these 2 together, it should all equal 0. Go.
All heat engines have an efficiency rating. This can be calculated by work out over Q in. What this equation tells us is the percentage of heat of the system that gets converted into working energy by the heat engine.
A car engine is a perfect example of a heat engine and the energy balance equation. In a car engine, heat is added to the system in the form of ignited fuel and air. This ignited fuel causes the piston cylinder system to decompress, producing work and spinning the wheels of the car. The piston then recompresses, which exhausts the ignited gas, thus finishing the cycle of the heat engine.
Bina bin, bina bin, bina bin, bina bin, bina bin, ha.